Thank you, Joe. I hope I sometime meet this amazing person you just described. Synesthesia comes from the Greek roots meaning union and sensation. And in individuals with this trait, stimulation of one sensation, let's say hearing a sound, induces something extra, an extra percept, often in a different sensory modality, such as vision. So in a very common form of synesthesia, which is called colored hearing, a specific sound, let's say C sharp played by a flute, will induce a specific color, blue. A different note, F sharp, might induce red. In other synesthetes, sound induces shapes. For one synesthete, this note on the flute might induce the perception of a star shape. In another synesthete, that same note might induce the perception of whirling swirls. And in a rarer form of synesthesia, that note might induce a taste, a highly specific taste. The taste of oranges, but not any old orange, an orange that is not quite ripe. Whereas our F sharp might induce the taste of mint. Now, there are many varieties of synesthesia. Franz Liszt, the famous composer, had color hearing. And when he conducted an orchestra, instructing them on how to play his own compositions, he was recorded as saying, "Oh, please, gentlemen, a little bluer, if you please. The tone requires it." The orchestra looked at him in bewilderment initially, but then they seemed to catch on and understand what he meant when he said a little bluer or a little redder, or this part is pink, and learned to follow his instructions. Another person with colored hearing and colored shapes is Carol Steen, whose works were exhibited at McMaster just over a year ago. When she hears sound, she sees colors and she hears shapes. And here's how she describes what was happening as she painted this composition. While I listened to Santana's version of a song called Aduma, I played this song over and over again as I painted the moving colors. So she's getting colors, she's getting shapes, and it's dynamic. It's constantly moving. In another common form of synesthesia, individuals see letters and digits in color. So while looking at black and white print, looking at a black 2, W, 5, P, 4, and H, they perceive color. And for an individual synesthete with colored letters and digits, this might be the color mapping. So the 2 and W are red, the 5 and P are purple, the 4 and H are green. It's a cross-cultural phenomenon. These are the colored characters of a Chinese synesthete. And in a rarer form of synesthesia, tastes induce tactile sensations. For one such synesthete, the taste of chicken induced the feeling of points. And when it was a very flavorful chicken, when I taste something with an intense flavor, the feeling sweeps down my arm to my fingertips, and I perceive that object as if I'm actually grasping it. Regardless of the form of synesthesia, synesthetes tell us their perceptions are automatic. They don't think about them, they just come. They've had them all their lives as far as they can remember. And their mappings, although idiosyncratic, that is, they're different from one synesthete to another synesthete, are consistent all their lives. They're consistent across years when tested in the lab. It also runs in families, telling us there must be a genetic component to this trait. So here is a family we've studied ourselves. The mother's colored palette is at the bottom. So what's shown there are the colors she perceives for the first few letters of the alphabet and the digits 1 to 9. Retested a year later, we get exactly the same colors. At the top is the color palette of her 4-year-old daughter. The first row is when we initially tested her at age 4. We came back and did it 4 months later, and then did it 3 months later. So you have 3 cycles of testing her for what she perceives when she looks at each of those letters and each of those digits. You'll note she has colored letters and digits just like her mother, but her color palette disagrees with that of her mother. And in fact, they have arguments that her mom is wrong about the color of certain letters of the alphabet. You'll also notice that there's a fair bit of consistency across the cycles in the colors that the child reports for those letters. Not quite as much consistency as we see in adult synesthetes, but much more than would be the case for those of us here who are not synesthetic when tested over such intervals. And you'll note also that she's highly particular. Look at the 4 in the middle cycle. It's purple and yellow. And it's particular purple and yellow. And she sometimes complained that even though we had given her a box of 300 crayons, the right color was not always in there for her to show us what color went with each of those letters and digits. Recent large-scale studies suggest that the incidence of synesthesia is about 4 to 5% of the general population, and it's equally probable in males and females. Now, I've called it a trait. People with synesthesia are fierce in telling us that it is not a disorder. In fact, they feel privileged. Their worlds are richer than the rest of us who don't have synesthesia. And here's a quote from a medical student who has colored hearing and colored letters. He says, "Let me say that it is a delightful trait to have. I tend to use it to help me remember correct sequences of numbers, words, phrases, letter, to help me remember names and locations of anatomical structures, especially neuroanatomical structures. You should see the beautiful array of colors in the brain and neuropathological classifications." And in fact, lab studies in the last couple of years have shown that individuals with synesthesia are superior in the domains related to their synesthesia. So people who have colored hearing or colored letters have indeed superior color vision to the rest of us, and have indeed superior memory for words and for colors than the rest of us. Okay? So it's not a disorder. It enriches lives and makes them superior in some domain. Okay, but we're scientists. This is all just people's descriptions of what they see. Is this fantasy or is it real? Scientists in the last decade have brought synesthesia into the lab to show that it is real. And one demonstration is these extra percepts in synesthesia work just like typical perception. So if a synesthete tells us that when I see a black tube, I perceive red, that black tube for that synesthete acts just like a red tube would for all the rest of us. One demonstration is what's called the Stroop effect. Now, we all have a Stroop effect. What I've done there, the trick, is I've printed the color words in the wrong colors of ink. And your job is to ignore the words and say the color of ink. Let's try to do it, okay? Everybody all together now. Blue, orange, red, green, green, blue. Why are you so slow? Let's do these, okay? Same job. Red, green, red, green, red, green, green, red. Or whatever color that green is showing up as there. what's happening here is even though I've told you to ignore the words, that they're just distractors, you can't do it. You automatically read them, and they interfere with your naming of the color of ink. Here, where I haven't set up any incongruity, there's no problem. We can do it very, very quickly. Now let's give the same task to an individual who reports that the black 2 looks red and that the 5 looks green. That individual, the first 4 that I've printed there, will be very easy and be very fast because they're congruent with the synesthetic percept. The last 4 I printed there will be very hard because I've printed the numbers in the wrong color of ink for that synesthete. That pattern of facilitation, faster on the left, slower interference on the right, indicates that the report that 2s cause me to see red and 5s cause me to see green, those are real percepts that are occurring in this individual. Here's another example. Anybody found the shape? A few of you. Now, if you were a synesthete for whom 2s and 5s induce different colors, it would have popped out at you. You would have instantly seen that there's a triangle formed by the 2s. If you don't have different colors induced by the 2s and the 5, this is laborious. You find 1, 2, and then you can go right, find another. It takes a long time to do this. Whereas for the synesthete, with colored digits, it just pops out. So one indication of the perceptual reality of synesthesia is that we get the same pattern of facilitation and interference on behavioral tasks as we do with real-world stimuli. A second kind of evidence comes from imaging studies that shows that these synesthetic extrapercepts evoke activity in the same parts of the brain as occur in everyday perception. So this has been done with functional magnetic resonance imaging, which essentially is looking for the parts of the brain that are active while we're doing a task by seeing where there are changes in the oxygen content of the blood. Areas that are active need more oxygen, and so by monitoring changes in oxygenated blood, we get an indication of what parts of the brain are active while individuals are doing different tasks. Now, for background, you need to know that at least by the time we're adults, we have highly specialized sensory cortices. So here is a map of the brain. It's color-coded, and I've put pictures by 3 parts of the brain. If you look back there at the back of the head, it's called the occipital lobe, and there's an eye. Neurons in that area respond when we see visual stimuli and do nothing at all when we hear sound or experience touch. They're specialized for vision. Neurons in the middle, in that area I've marked with the ear and auditory cortex, are active when we hear sound, but do nothing at all when we see something or are touched. And the third area up there, you can guess by now, somatosensory cortex with the hands. Neurons in that area are active in response to touch, but not sound or sight. So we have highly specialized sensory cortices, and then there are other areas higher up where information gets integrated across the senses. Now, when we put into the fMRI machine someone who has colored hearing and place sounds in the scanner, we see activity in all the normal areas for the processing of sound. But we also see activity in the color area V4, which is at the back of the brain in that area marked by the eye. We see activity in a visual area in response to sound. Similarly, if someone is in the machine who reports colored letters, and we present letters in the scanner, we will see activity in all the cortical pathways normally involved in the processing of letters, plus in color area V4. And the same pattern of activity in expected areas for the expected percept has been found for other forms of synesthesia. So, the behavioral evidence and the neuroimaging evidence have convinced the scientists that this is a real phenomenon. Where does it come from? To answer that question, we need to go backwards into infancy. And we need to know that initially, those sensory cortices are not so specialized as they are going to become in adulthood. Instead, there are transient connections among the sensory cortices that are going to get pruned away during development. For example, in baby monkeys, there is a connection between the auditory cortex down here and an area in the visual cortex called V4, that same color area that we've been talking about. During the development of the monkey, by the time the monkey grows up to have an adult brain, that connection is pruned away. This appears to be a ubiquitous phenomenon across mammals. Initially, the sensory cortices are not so specialized as they will become. There are transient connections between them. And we have some indirect evidence from human infants that those transient connections are functional, influencing the baby's perception. We know these from studies that have done EEG recordings, electroencephalography. So here, electrodes are placed all over the baby's head, stimuli are presented, recordings are made to see where there are changes in brain activity that are locked to turning on and off the stimulus. And of course, we can do the same thing with adults for comparison. Now, when we do this with adults and collect what are called evoked potentials, they're called evoked potentials because they're the potentials evoked by a particular stimulus. If the stimulus is sound, in particular, if it's speech, there's a change in the brain waves over the auditory cortex, but nothing happens over the other sensory cortical areas. Same experiment with young infants. There's lots of change in brain waves over the auditory cortex, but every bit as much change over the visual cortex. In the baby, the visual cortex responds to sound. Let's take another example. In adults, stimulating the hand causes a change in brain waves over the touch cortex. Technically, it's called the somatosensory cortex. Turning on white noise in the room at the same time doesn't do anything to the responses in the touch cortex. It's not responding to sound. Same experiment with newborn infants. Touch the baby's hand. There are changes in brain wave. There's activity over the touch cortex. Turn on the white noise. Turn on the sound. There's even a greater response in the touch cortex. The touch cortex is responding to sound in the newborn baby. So what we seem to have during early childhood is functional connections among sensory cortices. And the working hypothesis for what happens in synesthesia is that some of those extra connections remain. They remain and influence perception. What happens to them in the development of people without synesthesia, and to some extent even in individuals with synesthesia, is they get pruned away by experience. So I've tried to represent that by this diagram here. So we have a newborn baby up there at the top, typically asleep, where the visual cortex responds to vision, to hearing, and to touch. The baby gets visual experience through the eyes. That visual experience is strong, is coherent. It causes a lot of neural firing in the visual cortex. Neurons in the visual cortex continue to respond to vision, but the other connections to hearing and touch get pruned away. Because sound and touch don't do as good a job of stimulating those neurons in the visual cortex. The ones that aren't used as much get pruned away. The ones that are used are strengthened and remain. And we know this mainly from studies of babies who were born blind, who never get that visual input to the visual cortex. And that's what I'm representing in this cartoon. I've crossed off the eyes because there will be no input from the eyes to the visual cortex. But there will be input from the ears and from the skin to the visual cortex. And when these babies grow up, in adulthood, their visual cortex responds to sound, responds to touch, and is used in auditory and tactile perception. So, in the normal course of events, it's our experience that prunes the extra connections and gives us that highly specialized cortex. So what we think happens in synesthesia, so what we think happens in normal development is on the left. There's experience, pruning. We end up with a specialized cortex and no synesthesia. What we think happens in synesthesia is on the right, less pruning and synesthesia. And the red check mark refers to the fact that there's just been a study that shows that yes, indeed, there are more anatomical connections among sensory cortical areas in synesthetes than there are in non-synesthetic adults. But I haven't told you the whole truth. I just told you all those extra connections get pruned away. And we end up with these highly specialized sensory cortices. It's not really true. Most of them get pruned away, but some of them remain. And I've just given you this little dotted lines over there to represent that. Some of them remain, and they continue to influence our perception. Most of us don't have synesthesia, but we still have these synesthetic influences. I'm going to give you 2 examples of those synesthetic influences. Let's start with colored letters and digits. Remember, for synesthetes, looking at a letter induces the perception of a real color. If you don't have synesthesia, probably 5% of the people here do have synesthesia. So if you do, you can't play these games. That's cheating. I only want the people who don't have synesthesia to play these games. I just want you to tell me what color you think goes best with each of these letters. So just think about it in a minute, and then I'm going to see if we can get some kind of consensus. Okay? So what color goes with A? I heard red. Blue. I heard blue. How many people think red? Okay, I think red's going to win over blue, but there are some blues. How about the G? What color goes with G? I hear green and yellow, and I hear 1 blue. Okay, how many people think green? I think green's going to win. How about the O? Orange, white, yellow. How many people think orange? How many people think white? Did we miss any? So there are a lot of oranges, and there are quite a few whites, and then there's some scattered other ones. How about X? Black. How many people think black? Okay, how many people think purple? Green. Okay, we've got scattered responses, but a lot of you said red for A, G for green, yes. Green for G, Orange or white for O, a lot of blacks for X. Where do these associations come from? Well, some of them seem to be based in our language. A is for apple, apples are red, so A is red. G's are green, that's the first letter of the word. O's are orange, but why are O's white? Why are X's black? Well, to probe the origin of these associations, we've done some studies with toddlers. And they were motivated by reports in the literature that if you ask individuals in a whole bunch of different countries, speaking a whole bunch of different languages, to play the game you and I just played, but much more controlled in a laboratory, there's a pretty good consensus, far exceeding chance, on these mappings right there. To find out where they came from, Farron Spector and I went back and studied toddlers. Why toddlers? Because they don't know how to read. Some of them know some letters of the alphabet, but they don't know how to spell the word green. They don't know that the letter G is the first letter of the word green. And we devised a game to play with them. So we would show them a box. Let's say it's the one over there on the right, where half of the box is black and half is white. We would pick up an X out of clear plexiglass and say, I'm looking for my friend the X. X's look like this. Where do you think my friend the X is hiding? And we had some checks, what we call validity trials, to make sure the child was playing our game. I'm looking for my friend the snowflake. Snowflakes look like this. Where do you think the snowflake is hiding? And the kids had to search on the white side, or we thought they aren't really playing our game. But Farron is very good with toddlers, and almost all of them passed the validity checks. So we could look at the interesting data from the letters, where there's no right or wrong answer. And because there's no right or wrong answer, the child found an X, whether they searched on the black side or the white side. They got rewarded that they were correct. And what we found over a series of studies is that I's are white, O's are white, X's are black, Z's are black, and C's are yellow. And that's true if you're 2.5 years old. It's true if you're 7 to 9 years old and have learned to read. And it's true if you're one of the adults who came to the lab. All three of those populations agreed on these color choices. In a subsequent experiment, which we did with I, O, X, and Z, we discovered that it's the site, the shape of the letter that's driving this. So in this case, one group of children heard, I'm looking for my friend who looks like this. And they made all of these mappings. Another group of children didn't get to see the shapes. They heard, I'm looking for my friend the X. Where do you think my friend the X is hiding? They performed randomly. So we know the associations are being driven by the site of the shape of the letter, not its sound. And so we concluded that there seemed to be some natural associations between shape and color in individuals without synesthesia. They're present in pre-literate children. They're not based in any obvious way on learning. And they mimic synesthesia. So in individuals with colored letters, they're highly idiosyncratic, except they almost all will agree on these particular colors. So we think this mapping between shape and color is part of the intrinsic wiring of the nervous system. That's not the only pattern we found, though. When we tested children in the same way with these pairings, the toddlers failed. They performed randomly. It was only the older children and adults, all of whom knew how to read, who told us A's are red, B's are blue, G goes with green, and Y goes with yellow. So there are obviously additional associations that are learned, that change with literacy as letters take on meaning when a child learns to read. And they're therefore based on experience. So we need to modify the diagram I showed you before. In early childhood, it's true, there are extra functional connections between sensory cortical areas, many of which are pruned away, but some remain, even in individuals without synesthesia. We normally inhibit them. We don't go around the world, most of us, seeing white whenever we see an I printed in black. We don't go around the world seeing yellow when we see a C printed in black. So those connections are being inhibited, but they remain as cross-modal influences on our associations. The story in synesthesia is a little bit more complicated too. They start off with those extra functional connections. There is less pruning. We have evidence for that. So that more of the connections remain than in non-synesthetes. But there's also seems to be some kind of disinhibition. So those remaining connections aren't as strongly inhibited as they are in non-synesthetes. And the red check mark there is from some indirect evidence we have for this. You can take anybody, give them an hallucinogenic drug like LSD, and induce synesthesia. So take someone who came down the left stream, give them a drug that reduces inhibition, and they report synesthesia. Let me give you one more example of these cross-modal influences in all of us. And again, if you have synesthesia, please don't play this game. Okay, this one is related to colored hearing, a very common form of synesthesia. So here we have two balls. One, when it bounces, goes bing, and the other, when it bounces, goes pong. Which one goes pong? How many people think it's the white one? How many people think it's the black one? Why? Where does that come from? Well, we tested toddlers on this one too. We played which one is making the sound game with them. They saw the balls going up and down the screen, sometimes going ping, sometimes going pong. The speaker was coming from the middle. The speaker was not cueing which ball was making the sound. And then on the critical test trial, we played, for example, ping, said which one made that sound. Every single child pointed to the white ball. On another test trial, we said which one made the pong. Every single child pointed to the dark one. So even in toddlers, and toddlers have had some experience, but they don't know all the metaphors of our language. This is there even in toddlers. So there seems to be a natural association between lighter and higher pitch, between darker and lower pitch, present in non-synesthetes and also present in synesthetes. And that's illustrated over there on the right. So this is an individual synesthete with colored hearing being tested with the scale that's shown at the bottom and being asked to choose the color that goes with each note on two different runs. And as you can see, the colors go from brown through red, orange, and yellow. But they get lighter. As the note goes up in pitch, the colors get lighter. And that is true across synesthetes and across non-synesthetes. So here's a graph of the results for a group of synesthetes. On the y-axis is lightness. So a lighter choice is towards the top, a darker choice is towards the bottom. At the bottom is the note that was being played. For both groups, higher pitch goes with lighter. And this association influences your perception unconsciously. We know this from a clever experiment that was done by Larry Marks, which I'm simulating here with images. So your job is every time the bright light comes on, you're to push the button over here, and every time the dim light comes on, you're to push the button over there. And you're just to go as fast as you possibly can, and it's a really boring task, but you're just, you're being paid, so you're going to do a good job of it. There's a distracting noise in the room. And the distracting noise has two different pitches. It can be at the higher pitch or the lower pitch. And what Larry Marks found is if the correct answer was, this is the brighter light, push this button, and on that trial, the noise had the higher pitch, subjects were faster and more accurate. If on that trial, the distracting tone had the lower pitch, subjects made more errors, and their reaction times were a lot longer. So here, your perception of the lights, your ability to process that and do the task, is being influenced by this mapping. Brighter goes with higher pitch, darker goes with lower pitch. And so, to summarize, we start off with extra functional connections about sensory cortical areas, many of which get pruned away, but some of those remain in all of our brains. In those of us without synesthesia, they're being inhibited. So we don't get the conscious perception of these extra things. But those connections still influence our cross-modal associations and even unconsciously influence our perception. In the synesthetes, there's been less pruning, there's less inhibition, and those connections give rise to actual extra conscious perception, a trait that they value that enriches their perceptual world. And I should have had another box to indicate that, of course, in addition, there are learning influences that modify the cross-modal associations in both non-synesthetes and synesthetes. The work I've told you about that came from my own lab was conducted by many individuals. I hope I've remembered to put all of them on the list there. And we couldn't do it without funding from the Natural Sciences and Engineering Council of Canada. So I would be happy to answer questions. If you'd like to learn more about synesthesia, if you have synesthesia and you'd like to volunteer to be in one of our studies, we'd love to hear from you, and that's how to get in touch with me.